This is the concept of statistics, and from Lincoln University. This is from Lincoln University College. So the statistics is asked with the question, why do we study it? Because data are everywhere, and statistical techniques are used to make many decisions that affect our lives. And no matter what your career is, like nurses, they say nurses don't do numbers. No matter what the career is, everyone does numbers. And you will make professional decisions that involve data and understanding of statistical methods that will help you make decisions effectively. That's why we are studying statistics. And statistics is the science of collecting, organizing, presenting, analyzing, and interpreting data to assist in making more effective decisions. The statistical analysis is used to manipulate, summarize, and investigate data so that useful decision making information results. Okay, so that is also one of the reasons why we are doing statistics. And the types of statistics are descriptive and inferential. Okay, first, the descriptive. This is the methods of organizing, summarizing, and presenting data in an informative way. And the inferential statistics, inference means diagnosis. So descriptive means describing. So in an informative way, you have to describe it. The inferential means the diagnosis or determination on something about a population on the basis of a sample. That is an inferential. The population or the entire set of individuals or objects of interest, or the measurements obtained from all individuals or objects of interest. And a sample is a portion or part of the population of interest. So you have already discussed these on your quantitative research method last semester. And inferential statistics means diagnosing, using numbers, diagnosing it with the use of numbers. Alright, so these are the population of all items. Okay, and this is the sample item selected from the population. So the entire population is big, and the samples are only selected. Okay, so inferential statistics estimation estimate the population mean weight using the sample mean weight hypothesis testing, and test the claim that the population mean weight is something that exists. So an inference is a process of drawing conclusion or making decisions about the population. So that is what you call inferential statistics. You're trying to diagnose and then make decisions about your diagnosis based on sample results. So a sample should have the same characteristics as population it's representing. You cannot have a different sample and a different population. And with replacement, a member of the population may be chosen more than once, picking the candy from the bowl. This is the replacement. Without replacement, a member of the population may be chosen only once, like a ticket lottery. Thus, a sampling method can be random and non-random, or probability and non-probability sampling. And each member of the population has an equal chance of being selected in a random or in a probability sampling. But in a non-random or non-probability sampling, there are lesser chances of being selected. The actual process of sampling causes sampling errors. For example, the sample may not be large enough or for to be represented by a population. And the factors not related to the sampling process cause non-sampling errors. A defective counting device can cause a non-sampling error. So non-random sampling methods, simple randoms. This is the non-random. The simple random. Sorry, this is the random sampling. This the probability sampling. Number one is the simple random, stratified, cluster, and systematic. These are the probability sampling or the random sampling methods. So the simple is each sample has an equal chance of being selected. Stratified sampling is the divided population into groups called strata, and then they take a sample from each stratum. Cluster sample is dividing the population into the strata, clustering them. There's so in simple random you just choose anybody you want, but you have to give them equal chances. Stratified, you have phase 1, phase 2, phase 3. Like in COVID-19, that's phase 1, phase 2, phase 3 sample. Cluster sample, you cluster them into male, female, first floor of the hospital, second floor of the hospital, cluster 1, cluster 2, cluster 3, cluster 4. It depends on how do you group them together. And then there's an equal chances of being selected also in that cluster, but it is divided. The systematic sampling is the randomly selecting from a starting point to every piece. So, for example, every every second population will be selected. So you have to choose every third. You have to choose 1, 2, 3, 1, 2, 3. Population 1, 2, 3. Select this. This is the sample number 1, sample number 2, sample number 3. That's what you call systematic sampling. So there is a system. So the descriptive statistics uh, for the descriptive statistics, you have to collect data and the survey and present the data. Examples are tables and graph. This is the statistics that is descriptive. The graph and the tables, okay, they are just showing you frequencies and percentage. The video that I showed you is also descriptive statistics when we trying to watch how to do only the percentage of the description and then summarize the data. Example of summarizing is mean. Mean is the summation of all the population divided by the number of population. So you sum it all up, divide it, average, and then that is called the mean. Statistical data, the collection of data that are relevant to the problem being studied, is commonly the most difficult, expensive, and time-consuming part of the entire research, which is the statistical data. Okay, statistical data are usually obtained by counting or measuring items. Primary data are collected specifically for the analysis desired, and secondary data have already been compiled and are available for statistical analysis. A variable is an item of interest that can take on many different numerical values. A constant has a fixed numerical value. So these are the terminologies that you need to remember. Primary data, secondary data. The primary data are the one that you collected yourself, and the secondary data are the ones that has been collected for you. Primary data is your survey questionnaire. This is your research survey questionnaire. Secondary data is something that is already there and then you just count it. For example, of your primary data is your survey questionnaire, you give it to them, you collect it, and then you count it, and then you put it on statistical approaches. An example of secondary data is like the nationwide study of basic life support, whether they want to prove if AED is effective or not. They don't collect it, okay? They don't collect it. The ambulance will collect it for them. They will note there what they did. Did they put AED or did they not give AED? And then from the record book, all you have to do is calculate. Get the record book and then collect it, and then you have already the secondary data. Or patient profile. They have in the hospital, they have the statistics logbook of all the cases and the number of populations. They did not collect it, the wards or the department wards from the hospital ward. They have done the data collection. They submit it to the director, and that director is receiving secondary data already. Somebody collected for them, and then they're gonna put it on the National Statistics Office of Malaysia, and then they'll tell you how many COVID-19 cases you have. That's also a secondary data. Why? Because not the researcher cannot resuscitate the whole country by himself. Okay, so what the researcher will do is will go to the statistics of the all the ambulances that he has connected with, and then get all those profiles of those who died out of hospital in cardiac arrest, and then they will just take all the data and then put it in their SPSS and then calculate it, and that is called an observational study. Okay, an experimental observational study. uh, the one that you can primary collect is you yourself has done it. Somebody else done it for you. You just transfer it to your SPSS. That's called the secondary data collection. You're not. You didn't do it. Like for example, the exposure to radiation, all the blood tests you sent the laboratory, and the laboratory does their primary data collection, interpret it, give you the number of hemoglobins and hematocrits and the exposure for WBCs. When you're sending blood tests to the laboratory, they send it back to you, the results. You did not collect that. You're not the one collecting it primary. You're just a secondary data collection. Okay, you can do that for um, you can do that for statistics as well. Statistical data are usually obtained by counting or measuring item, and most data can be put into following categories: qualitative and quantitative. So, qualitative can also have a data, all right? A simple data, how many is the hair color of the ethnic group, attributes to the population, or a simple qualitative data can also be uh, having a mathematical percentage. Quantitative data are observations that are measured on numerical scale, traveled college number of children in a family. So that's also a quantitative data. That's a measurement. Qualitative data usually has case study. Case study is a qualitative design. A case study is a qualitative design. So in your case study, usually you have mathematics here or measurements. Some are the hemoglobins, hematocrits, or the swab test, culture and sensitivity, how many PMNs, how many in the fecalyses, in the urinalyses, what is the specific gravity. Okay, those are the quantitative measurements, all right? Or the hair color, you know, that is a qualitative case study design that needs mathematical measurements. But it doesn't mean that you can conclude mathematically. Qualitative data are generally described by words or letters, and they are not as widely used as quantitative data because many numerical techniques do not apply to the qualitative data. For example, it does not make sense to find an average hair color, blood type, or qualitative data can be separated in subgroup dichotomic and polynomic. So the dichotomous, if it takes from a word with two options, gender or female or male, those are the dichotomous. Polynomic, if it takes in the option of two or more, like education, primary school, secondary, and university, you have also all these um, demographic data for qualitative, and they can be numerical. So the quantitative data are always numbers and are the results of counting or measuring attributes of a population. The quantitative data can be separated into two groups: discrete or continuous. So the quantitative can be discrete or continuous. If it is the result of counting the number of students given an ethnic group and the number of a class, then it is discrete. Continuous is a result of distance traveled, weight of luggage. Those are the continuous um, with measurements of kilometers per hour or BMI, that's continuous, or the distance. So the types of variables can be qualitative and quantitative. These are one of the statistical variables. This is not um, the research variables, the statistical variables on qualitative and quantitative. The qualitative can be dichotomous or polynomic. Dichotomic or polynomic. And quantitative can be discrete and continuous. So, when you're having two gender status is only two, then dichotomous, male and female. If the gender becomes three, then it becomes polynomic. So the marital status, for example, they have married or unmarried, or there are a lot of dichotomic variables, statistical variables for qualitative. Polynomic is more than two, three or more. So the quantitative statistical variable is discrete and continuous, like children in family strokes on a golf hole, or amount of income tax paid, weight of a student. Those are the statistical variables, not research variables, because the research variables is an independent variable. But for statistical variables is the dichotomy, polynomic, discrete, and continuous. So the numerical scale of measurement can be nominal, ordinal, interval, or ratio. This will be asked from your SPSS. Is it nominal, ordinal, interval, or ratio? Okay, it consists of categories on each of which the number of respective observations is recorded, and the categories are in no logical order and have no particular relationships. And the categories are said to be mutually exclusive, since an individual object or measurement can be included in only one of them. The ordinal contains more information and consists of distinct categories in which order is implied. Values in one category are larger or smaller than values in other categories. While the interval is a set of numerical measurements in which a distance between numbers is of a known constant size, and the ratio consists of numerical measurements where the distance between numbers of a known and constant size in addition, and there is a non-arbitrary 0 point. So the ratio has 1 is to 2, 1 is to 1. The interval has the set of numerical measurements with the distance in between them. They have interval distance. The ordinal is in the order of the rating of excellence, such as good, fair, and poor. Not just the rating of excellence, but in the order of um, disagree, agree, neutral, strongly disagree, strongly agree, or strongly agree, agree, neutral, strongly disagree, and disagree. Those are the order, in the order of, that's what you call ordinal. The nominal has just the numerical setting, the mutually exclusive numerics. The nominal is only the numerics that you have with no particular relationship to each other, and it's just a number, like true or false, yes or no. But when you put maybe, yes, no, maybe, it becomes in the order of. The first is the no, the next is the maybe, and the last is the yes, or in the other way around. So that's what you call the ordinal. If you want it in the order of, and it's the ordinal. I don't know how to do statistics, but it doesn't matter because I didn't have a data. So you must have a data. Numerical presentation of qualitative data can be pivot table or contingency table. There's a table for this, only a table for numerical presentation of qualitative data, not so much. Frequency distributions, numerical representation of quantitative data, the frequency can be when you're trying to present it, we're trying to show it in a figure. It can be on a graph, on a bar, on a table. There's a lot of frequency distribution numerical representation of quantitative data. it can be in a bell curve shape or histogram. Okay, it doesn't matter how you represent it, but quantitative has more distributions. So steps for constructing a frequency distribution: determine the number of class, determine the size of each class, determine the starting point for the class, tally the number of values that occur in each class, and prepare the table of distribution using actual counts. Alright, that's how do you do it. Frequency table. So the absolute frequency is called the small n. Alright, the relative frequency is the f1. That's called the f1. So when you see a small n, that's an absolute frequency. Cumulative frequency is big letter N. And cumulative relative frequency is the big letter F. That means this is the universe or the population, and the bigger frequency is the entire frequency of the whole population if is F. What you chose, the sample size is small letter n, and the frequency of the small letter n is the small letter f. Charts and graphs. Frequency distributions are good ways to present the essential aspects of data collections in concise and understandable terms. Pictures are always more effective in displaying large data collections. So these are the charts and graphs. The histogram, frequently used to graphically present interval and ratio data, and is often used for interval and ratio data. The adjacent bars indicate that a numerical range is being summarized by indicating the frequencies in arbitrarily chosen classes. So this histogram executive incomes for the Sunrunner Corporation is a quantitative representation. So the frequency polygon is another common method for graphically presenting interval and ratio data. To construct a frequency polygon, mark the frequencies on the vertical axis and the value of the variables being measured to the horizontal axis as with the histogram. So I'll show you on SPSS how to mark that. If the purpose is presenting is comparison with other distributions, the frequency polygon provides a good summary of the data. So you just have to mark this. It's so easy to do this because all you have to do is click, 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 and then put where the X should belong to. You can mark them. Where is your diagnosis? Is this your diagnosis or this is your diagnosis? So all you have to do is mark them so that the polygons can be easily interpreted. The O-give is a graph of cumulative frequency distribution. So this is an option, an O-give is an option. It's used when one wants to determine how many observations lie above or below a certain value in a distribution. First, cumulative frequency distribution is constructed, and cumulative frequencies are plotted at the upper class limit of each category. The O-give can also be constructed for a relative frequency distribution. Okay, O-give executive incomes. This is an O-give. All you have to do is mark it. An O-give is like a curve. It's not really a spike one, but a curve. It's just a representation. Pie chart is a pie divided into 100% into smaller portions of 100%. So there's no pie that is more than 100%. That is the weakness of a pie. It has to be divided. If you divide into 2, therefore it's 50-50. That's a pie. You cannot have 60-70 or 80-90. Only 100%. And useful if the relative size of the data components are to be emphasized. Pie charts also provide an effective way of presenting ratio or interval scaled data after they have been organized into categories. A pie chart here, you can always assume that this is 100%. Do not look at it as less than 100% because, or more than 100%, because a pie has to be 100%. The bar chart, another common method for graphically presenting nominal or ordinal scale data. One bar is used to represent the frequency of each category, and the bars are usually positioned vertically with their bases located on the horizontal axis of the graph. The bar are separated, and this is why such graph is frequently used for nominal or ordinal data. And the separation emphasizes the plotting of frequencies for distinct categories. This is a bar chart. You can also use this to represent your data. Alright. So there's a lot of options for you to choose your... The time series graph is also an option. The time series graph is a graph of data that have been measured over time, and the horizontal axis of this graph represents time periods, and the vertical axis shows the numerical values corresponding to these time periods. So these are the time series graph. Okay, it's showing the time because the time is down here on the horizontal axis. You can show them the time series. What I do when a teacher says this cannot be done, so this is also a graph that shows how you have to represent your mathematical expressions. Okay, so that is statistics.
Some numbers aren't actually numbers. In statistics, data lives in two main families, categorical and numerical. One describes what kind, while the other describes how much. Categorical data comes in two flavors. First, nominal, like the variety of an apple. Gala, Fuji, Rose is just a name and the order doesn't matter. Then there's ordinal data where the order is everything. Think of a star rating. Poor is less than excellent. It's still a label, but it has a specific rank. Now let's talk numerical data. Discrete variables are things you count in whole chunks, like website clicks or car accidents. You can't have half a click, so we visualize these with bar graphs. But continuous variables, they can be anything. Temperature, distance, or time. Because they can be infinitely subdivided into decimals, we use smooth line graphs or histograms to see the flow. Here's the golden rule. If it makes sense to calculate an average, it's numerical. If the number is just a label, like a zip code or a jersey number, it's actually categorical.
You have data on a piece of paper that you need to get into Excel. The first thing you have to do is open up Excel on your phone. Then you're going to tap blank workbook. Then you want to click on a cell. Then tap on the three dots in the bottom right. Click on home, insert, and then data from picture. Now your camera should open. All you have to do is take a picture of your paper. Make sure the edges are selected and hit confirm. Now you have your data in Excel on your phone. And now you can see if I send a copy to my computer, I'll have all the data.
Look at this crowd. Everyone has a completely different height. How do we make sense of this chaotic, continuous data? We use a histogram. Instead of a messy crowd, we sort everyone into distinct, touching ranges on an axis. Watch how they stack up. But what if we want to ignore the individual people and just see the overall shape of the crowd? We drop a dot at the top center of each column and connect them with a line. This is a frequency polygon. It transforms those clunky stacks into a smooth, readable curve. But there is one massive blind spot here. These charts completely ignore time. What if we want to track rising temperatures over the decades? That is when we use a time series graph. By putting years on the bottom axis, we track the exact timeline of a single variable. Watch the temperatures rise. The line connects the data to reveal an undeniable upward trend. Histograms for continuous groups, polygons for smooth shapes, and time series for tracking history. Look at this raw data. Just staring at rows of numbers is a nightmare. To actually understand what this means, we need to give the data a shape, but pick the wrong graph, and the story is lost. First, when do you use a bar graph? Use it when you have categorical data. If you're comparing distinct groups, like who sells the most coffee between a Starbucks, Dunkin', and a local cafe, bars let you instantly see who is winning the race. But what if your numbers are tracking something over time? That's when you use a line graph. Watch Bitcoin's wild ride over the last decade. The line literally follows the price point, connecting the dots to reveal trends and volatility that a bar graph would completely miss. Finally, what if you have a small set of exact scores and you can't afford to lose a single digit? Use a stem and leaf plot. The stem groups the tens and the leaves grow out to show every exact raw number. It keeps the microscopic details alive. Categories get bars, time gets lines, details get stems. We have looked at single variables, but what if we want to see how two completely different things relate to each other? We use a scatter plot. Let's look at global GDP per capita versus life expectancy. Every bubble is a country sized by its population. Ever wonder why the average height often hides the most interesting part of the data? In statistics, the mean is just the starting point. To truly understand a group, we need to measure the spread using variance and the standard deviation. Take these 6 friends. To find their average height, we add them all up. 150, 160, 145, 175, 155, and 145, obtaining a sum of 930, which we then divide by our count of 6 to find a mean of exactly 155 centimeters. Now, look at the distances from this yellow line. These are called deviations. And the bigger these arrows are, the more spread out the group is. To find the variance, we square these distances and divide by n-1 for samples to stay unbiased, which gives us 130. We use n-1 instead of n because samples usually look less spread out than the whole population. And this tiny math adjustment gives us a much more honest estimate of the real world. Finally, we take the square root to find our standard deviation, 11.4 centimeters. This blue band shows the typical range, telling us exactly how much individual values tend to vary.
In this video, we're going to talk about how to calculate the variance and the standard deviation of basically a list of numbers. So the standard deviation and the variance tells us the spread of the data, like how far the data is from the mean. So let's talk about how to calculate the variance and the standard deviation for the first list of numbers that we had. So we're going to make a table. X is going to represent the data values, and then X bar will represent the mean of that data, and then X minus X bar, so the data values minus the mean, that's going to tell us the deviations. And then in the next column, we're going to have the square of the deviations. So the numbers are 6, 7, 8, 9, and 10. Now what we're going to do is we're going to take the sum of the first column. The reason for that is it's going to help us to calculate the mean. The mean is going to be the sum of the data values divided by n. So if we add 6, 7, 8, 9, and 10, that's going to give us 40. So that's the sum. The mean is going to be 40 divided by n. Now what is n? Looking at our list of numbers, we have 5 numbers in this list. So therefore n is 5. 40 divided by 5 is 8. So the mean is going to be 8, which we'll put in the second column. Now let's calculate the deviations. So this is going to be x minus x bar. So here it's going to be 6 minus 8, which is negative 2, and then 7 minus 8, which is negative 1, 8 minus 8 is 0, 9 minus 8 is positive 1, 10 minus 8, positive 2. Now, if we add up the deviations, negative 2, negative 1, 1, and 2, it's going to add up to 0. Now, the next thing we need to do is square the deviations. Negative 2 squared is 4. If you write it like this, this is negative 2 times negative 2. Negative 1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. Our next step is to add up the deviations. 4 plus 1 plus 1 plus 4 adds up to 10. Now, you need to know what this number represents. So that number is basically the sum of the square of the deviations. We're going to use that to calculate the variance and the standard deviation. Now the variance, represented by s squared, this is the sample variance. It's going to be the sum of the deviation squared divided by n minus 1. So we already know what this value is based on what we see here. That's 10. N is 5. There's 5 numbers in our list. And 5 minus 1 is 4. 10 divided by 4 is 2.5. So this is the sample variance of the data. So I'm going to write that here. S squared is 2.5. So that's how you can calculate the sample variance, or the variance of a sample. Now let's calculate the standard deviation. Here's the formula for the standard deviation. It's the square root of the sum of the square of the deviations divided by n minus 1. So the standard deviation is basically the square root of the variance, which we already have here. So it's going to be the square root of 2.5, which is approximately about 1.581. So now you know how to calculate the standard deviation and the variance of a sample. Now it's your turn. So using the second list of numbers that we had, 4, 6, 8, 10, and 12, go ahead and pause the video and calculate the sample variance and the sample standard deviation. Go ahead and try it. So let's construct the table first. So we have x, x bar, and x minus x bar, the deviations, and then the square of the deviations. So our x values are 4, 6, 8, 10, and 12. Now let's calculate the sum of the first column. So 4 plus 6 plus 8 plus 10 plus 12, that's going to be 40. So now let's calculate the mean. The mean is going to be the sum divided by n. The sum is still 40, and we still have 5 numbers in the list. So once again, the mean is 8. Now let's calculate the deviations. 4 minus 8 is negative 4. 6 minus 8 is negative 2. 8 minus 8 is 0. 10 minus 8 is positive 2. 12 minus 8 is 14. 12 minus 8 is 4. Now, if we add up this column, the sum of the deviations should always be 0. Next, let's calculate the square of the deviations. Negative 4 squared is 16. Negative 2 squared is 4. 2 squared is 4, and 4 squared is 16. Now, if we take the sum of those values, 16 plus 4 is 20. 4 plus 16 is also 20. 20 plus 20 is 40. So at this point, we have everything we need. We have the sum of the square of the deviations. So now let's calculate the variance. So the variance for this sample is going to be the sum of the square of the deviations divided by n minus 1. So the sum of the square of the deviations, we see that is 40. N is still 5, and 5 minus 1 is 4. So it's going to be 40 divided by 4, which is 10. So the variance is 10. Now our next step is to calculate the standard deviation, which is simply the square root of the variance. So it's going to be the square root of 10, which is approximately 3.16. It's like 3.
Why do statisticians care more about the middle of your data than the absolute edges? It's all about how we measure a spread. The range is the simplest way to do it. It's just the total distance from your absolute minimum to your absolute maximum. Imagine a street with 5 modest houses. The range looks tight and consistent. But add one massive multi-million-dollar mansion and the range stretches like a rubber band. Suddenly, your data looks way more spread out than it actually is. That's where the interquartile range, or IQR, comes in. Instead of being distracted by the extremes, we split the data into 4 equal parts, or quartiles. We ignore the bottom 25% and the top 25%, focusing only on the middle 50%. In our street example, the IQR stays locked on those typical houses, completely ignoring that outlier mansion. Use the range to see the full span, but use the IQR to find the heart of the data. It's the spread that outliers can't touch. How do you summarize 1,000 data points using only 5 numbers? Welcome to the 5-number summary. It's the ultimate X-ray for your data, giving you the minimum, the first quartile, the median, the third quartile, and the maximum. It tells the whole story at a glance. Let's look at exam scores. We start with our minimum and maximum. That's the full span of the class. Then we find the median, splitting the scores exactly in half. Next, we find the middle of those two halves, Q1 and Q3. These 5 numbers give us the skeleton of our data distribution. Now watch the magic. We draw a box from Q1 to Q3. This is your interquartile range, or IQR, containing the middle 50% of students. We add whiskers to reach the extremes. And just like that, you have a box plot. The box shows the heart of your data, and the whiskers show the full range. It's the perfect way to spot patterns without getting lost in the noise. Spot the odd one out. Look at this group. We have a few animals and a city bus. Even though they're standing together, that bus is clearly the odd one out. In statistics, we call this an outlier, a data point so extreme it sits far outside the normal patterns of the rest of the group. But as data scientists, we can't just guess. We have to prove it with math. Let's move our outlier aside and look at the fences. First, we find the middle 50% of our data, the interquartile range, or IQR. Here our first quartile, Q1, is at 2. Our third quartile, Q3, is at 4.5. That makes our IQR exactly 2.5. Now we calculate the fence to find the danger zone. We take Q3 and add 1.5 times the IQR. That's 4.5 plus 3.75, giving us a boundary at 8.25. Anything past this yellow line is officially a mathematical outlier. Our bus, sitting way out at 11, clearly qualifies. Identifying these is crucial because one extreme value can wreck your average. Scientists say p less than 0.05 means significant. But what does that really mean? A p-value is the probability of seeing data this extreme by chance alone, assuming the null hypothesis is true. Imagine we expect random results to follow this curve. Your actual result lands way out here in the tail. The p-value is this tiny red area. The smaller it is, the more surprising your result. Here's an example. You flip a coin 10 times and get 8 heads. Is the coin rigged? The p-value is 0.055, just above 0.05. Not quite surprising enough to call it rigged? Now imagine a medical trial. A new drug lowers blood pressure by 15 points. The p-value, 0.001, highly significant. This result is so extreme, it's very unlikely to happen by chance. But here's a common mistake. P equals 0.05 does not mean there's a 5% chance you're wrong. What it actually means is, if no real effect exists, there's a 5% chance of seeing data this extreme. Also remember, statistically significant doesn't mean practically important. A small p-value doesn't always mean a large effect. So why a 0.05? It's an arbitrary convention from the 1920s, popularized by statistician R.A. Fisher. It's called the borderline, but context matters. It's not a magical cutoff. Now you understand p-values. Remember, a p-value measures probability by chance. Small p means surprising results, and p less than 0.05 means statistically significant. What confused you about p-values? What do heights, test scores, and flipping coins have in common? They all form the universe's favorite pattern, the normal distribution. It all starts with mu, the exact average. In nature, most data naturally clusters right here in the middle. But how spread out is it? We use standard deviations, or sigma. 68% of everything falls within just one step of the average. Take 2 steps out, and you capture 95% of the data. Most of life lives exactly in this zone. Take a 3rd step, and you've captured 99.7%. Almost everything that exists naturally fits perfectly inside this space. So what about the remaining 0.3%? Those tiny tails are the extreme values, splitting into exactly 0.15% on each side. In a perfect world, data is balanced like this bell curve where the mean, median, and mode are all best friends sitting right in the center. But real-world data has a mind of its own. When it starts to lean, we call it skewness. Watch what happens when the tail stretches to the right. This is positive askew. The mode stays at the peak, but the mean is easily bullied by high outliers and gets dragged far away. In a negative askew, the tail stretches left, pulling the mean down with it. Now, look at the peak's intensity. That's kurtosis. When k equals 3, it's our standard shape. But when k is greater than 3, you get a leptokurtic spike, tall, sharp, and hiding extreme risks in its heavy tails. When k is less than 3, you have a platykurtic plateau, flat, stable, and spread out. Skewness tells you the direction of the lean, but kurtosis tells you the impact of the extremes. Stark attacks and ice cream sales spike together every single year. But here's the twist. Sharks don't actually cause ice cream sales. These statistical patterns come in a few distinct flavors. When one variable moves, the other moves with it. When X climbs, Y comes right along for the ride. Take studying. Every extra hour tends to pay off. Each dot is a real student, and the upward drift is unmistakable. Now flip it. The two variables push against each other. Late-night Netflix marathons paint this perfectly. Every extra episode chips away at your snooze time. But just knowing the direction isn't quite enough. We need a precise number. Enter the magnifying glass of statistics. One tiny letter does all the heavy lifting. Meet the gentleman who first dreamed up this number, Carl Pearson. Victorian era. Serious math swagger. Little r is humble, but ridiculously powerful. It boils every relationship down to one tidy value. Every value of r lives between two extremes. Watch the dot cruise across the entire spectrum. When r hits +1, the dots refuse to stray. Total predictability. Flip it to -1. Equally precise, just inverted. Then there's 0. Total disconnect. The dots are basically rolling dice. Real data never behaves this cleanly. A value like 0.6 is genuinely strong. Here's the big lesson. Correlation is not causation. Back to our sharks. It's the summer sun. Heat brings people to beaches and ice cream shops. The sun causes both.
Let's take a look at how different personal factors might be related to insurance charges. We'll use a quick correlation test in Excel to find out. First, head to the Data tab, click Data Analysis, and choose Correlation. Select your columns, in this case, age, BMI, number of children, and insurance charges. Hit OK and Excel will give us a correlation matrix. Now, let's break down what that means. Correlation values range from -1 to +1 and tell us how two things move together. Values below 0.3 are low, 0.3 to 0.5 are moderate, and above 0.5 are strong. So what do we see? Age has a moderate positive correlation with charges, meaning as age goes up, insurance charges tend to increase too. That kind of makes sense, right? But BMI and number of children both show low correlation with charges. So just having a higher BMI or more kids doesn't strongly affect how much you pay for insurance, at least based on this data set. And just so you know, a negative correlation means that as one value goes up, the other tends to go down, like exercise time and stress level, for example.
In this video, we're going to talk about how to calculate the correlation coefficient between two variables. But before we do that, let's talk about what the correlation coefficient tells us. So let's say we have a straight line and we have points on the line. The correlation coefficient will be +1 for this situation because all the points are on a line and the line has a positive slope. Let's say this is x and this is y. It's a positive correlation because as x increases, y increases. There is a direct relationship between x and y. Now here's another scenario. Here we have points on the line, but notice the line is going down. And so the correlation coefficient will be equal to -1. As x increases, y decreases. And so in that case, we have an inverse relationship. Now in this example, the points are not necessarily on the line, but they're close to it. And so these points, they have somewhat of a linear relationship, but not exactly one. So in this case, r is going to be somewhere between 0 and 1. It's positive because this line is increasing. It has a positive slope, but it's not exactly 1. If we were to put a number to it, it might be 0.8 or something. Whereas let's say if you have a similar line, but let's say the points are more scattered about that line, the r value will be less. It might be 0.7 or 0.6. It could be completely different, but it's somewhere between 0 and 1. But the point is this though. The closer that the points are next to the line, r is going to be closer to 1. These points, they're further away from the line, so r is going to be closer to 0 than 1 relative to this number. Now sometimes there won't be any correlation. Let's say if you have just random points everywhere. In this case, r could be very close to 0 for a situation like that when there's no apparent correlation. So the correlation coefficient really tells us the strength of the linear relationship between two variables. If these two variables have no linear relationship, r is going to be close to 0. If there is a strong linear relationship, r is going to be close to either +1 or -1, depending on the slope of the line. Now let's take a minute and calculate the correlation coefficient. So we're going to make a table containing the columns x y, and then the product of xy, and then x squared, followed by y squared. So for x, we have the numbers 1, 2, 3, 4, 5, and 6. So let's extend this a bit. Alright, now let's fill in this table. So next, let's put the y values, which are 2, 4, 7, 9, 12, 14. Moving on to the next column, we need to multiply x and y. So 1 times 2, that's going to be 2. And then if we multiply 2 and 4, we're going to get 8. Next, we're going to multiply 3 and 7, which is 21. And then 4 times 9, that's 36. 5 times 12 is 60. And then 6 times 14. 6 times 10 is 60. 6 times 4 is 24. When you add 60 and 24, that gives you 84. Now moving on to the next column, x squared. So we're going to square the values that we see in the x column. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. Now for y squared, all we're going to do is square the values in the y column. So 2 squared is 4, 4 squared is 16, 7 squared is 49, 9 squared is 81, 12 squared is 144, and 14 squared is 196. Now our next step is to sum up each column. So if we take the sum of the x values, it's going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6. That's going to be 21. Let me put this in a different color. Now let's take the sum of the y values. 2 plus 4 plus 7 plus 9 plus 12 plus 14. So that gives us a sum of 48. Now, we need to determine the sum of the product of x and y. So 2 plus 8 plus 21 plus 36 plus 60 plus 84. So that's going to give us 211. Now the sum of the x squared values, 1 plus 4 plus 9 plus 16 plus 25 plus 36. So that's going to be 91. And then the sum of the y squared values, 4 plus 16, 49, 81, 144, and then plus 196. So that's going to be 490. So this is the sum of the x values. 48 is the sum of the y values. And 211, that's the sum of xy. 91 is the sum of x squared, and 490 is the sum of y squared. So once we have those numbers in red, we can now plug in the information into the formula to get the answer we need. So I'm going to delete everything up to there. And here's the formula that we need. So the correlation coefficient R, which in some equations is represented by the Greek symbol rho, it's equal to n times the sum of xy minus the sum of x times the sum of y divided by the square root, and inside the square root it's going to be n times the sum of the x squared values minus the sum of x values, but we're going to square that. So be careful with that difference. And then it's going to be n times the sum of the y squared values minus the sum of the y values and then squared. So let's plug in everything into that formula. So it's going to be n. Well, we need to know what n is. And if you recall, there were 6 x values. 1, 2, 3, 4, 5, 6. So n is the number of values that we have in one single column. So that's 6 in this example. And then times the sum of xy, which is 211, minus the sum of the x values. So that's 21. And then the sum of the y values, that's 48. So at this point, we just gotta plug everything into this formula. And then it's going to be n times the sum of the x squared values, which is 91, minus the sum of the x values squared. So that's 21 squared. Then it's going to be n times the sum of the y squared values, which is 490, and then minus the sum of y, which is 48 but squared. So that's what we have so far in this example. Now let's plug everything in. So we can get rid of these numbers. Six times 211 is 1266. And 21 times 48, that's 1008. Now, 6 times 91, that is 546. 21 squared is 441. Now, 6 times 490 is 2940. And then 48 squared, that's 2304. Now let's subtract 1266 by 1008. So that's 258. And then we have 546 minus 441, which is 105. And then 2940 minus 2304, that's 636. So far we have r is equal to 258 divided by the square root. And now let's multiply those two numbers. So 105 times 636, that's 66,780. So if we take 258 and divide it by the square root of 66,780, we get an r value of 0.998. So this r value is very high. This indicates that there is a very strong linear relationship between the x and y variables that we have in this problem. And the fact that it's positive tells us that the slope is positive, that there's a direct relationship between x and y. As x increases, y increases. So that's basically it for this video.